Right. Great. Great. I want to welcome everybody to this Lunch and Learn to this Neurocarpentry's Lunch and Learn series. This has been a really great initiative that's been started for the past 2 years with people like myself, with JB, who's in the chat, who you can see in the side, at CAMH, sharing across multiple institutions, including McGill, including my institution, the Center for Addiction and Mental Health, Brock University, and Western University. And I have to give a special shout out to John and Michael, and John Legata, Michael Joseph, and Jason Kai, who are in the chat, who did a lot of work to put this curriculum together today. So you might have noticed that we are recording. Just to note that we are recording this specifically for you guys, so that we can send out these videos to people who may have registered and weren't able to join. So if you would not like to be in the recording, we do recommend that you turn off video and mute yourself. But we also very much encourage you to ask questions. So questions can be asked either in the chat or on our accompanying Etherpad that we'll be running during the day. And we'll be putting up the link to that Etherpad very quickly. Also, we want to thank John and Michael and Jason, who are in the chat, who will be answering your questions, as well as our 2 instructors. So hopefully there'll be a lot of good discussion happening there. We also strongly encourage you to follow along on your own computer. So we want to make it known that all of the materials that we teach in this series are available in the Software Carpentry GitHub series. So they can be cloned to your own computer, and if you want help installing these particular materials in your own computer, then you can speak to us in the chat or after the break. But while this is happening, we have everything also set up in Binder. If people haven't used Binder before, then it is a system where you can click on the link, and all of the software and data will be available to you in your browser tab. So you should be able to follow along right away with all of the materials by clicking on the link, and we very much encourage you to do so. Just a reminder of the amazing other courses that are happening in this series. Today we're talking about dMRI analysis in Python, but in the next 3 weeks we're going to be talking about resting state analysis and EEG. And if you're interested, if you have FOMO for the last 2 weeks, we do have the recordings available for our intro to MRI and BIDS and our structural neuroimaging and Python analysis. So without further ado, I would like to introduce our instructors for today. So we have 2 amazing instructors. The first is Bradley Karat from University of Western Ontario. He's a PhD candidate at Western University, supervised by Dr. Ali Khan. His current research predominantly uses diffusion MRI to probe complex microstructure in the hippocampus, a brain region known to deteriorate with neurological diseases and Alzheimer's and epilepsy. And our second instructor is Davide, who you hear from, Davide Mome. He completed his PhD at the University of Chieti. I don't know how good my Italian is. And he attended a period abroad at the Martino Center for Biomedical Imaging at Harvard Medical School. His main interest is focusing on predicting the TMS signal propagation at the network level based on neuroimaging and electrophysiological data. So he's currently a first-year postdoc at the Crumble Center for Neuroinformatics, which is my cool Zoom background and his real Zoom background at the moment. And he does whole brain modeling as well as analysis and modeling of TMS evoked responses. So with that, I will turn it over to our 2 amazing speakers.
All right. Thanks, Erin, for the introduction. I'm gonna share my screen. All right. Yeah. Can you see my screen? All right.
Yep, we're good.
With the code. Awesome. So, yeah, as Erin was saying, today tutorial is gonna be on diffusion MRI in Python. This is gonna be the outline of the lecture. and we are gonna basically move directly. I think all the participants might have the link already at this point, so I'm gonna go ahead and move directly to the basically the syllabus and moving to the introduction with diffusion MRI. So yeah, basically yeah, the diffusion MRI, as you might know, I mean, the brain, we have basically different tissue, which are basically gray matter, white matter, and CSF mainly. And basically, the white matter is made by axons, and those axons are basically in the order of microns. However, of course, we don't have basically the spatial resolution in vivo with MRI to image every single of these axons. So, however, we are lucky because rather being kind of a mess, these axons are basically arranged and organized in a bundle and tend to be basically parallel each other, right? Especially in the regions like corpus callosum, they are really, I mean, oriented in a certain way. And this orientation basically allow the fiber to travel and connect brain regions all together. So even though we don't have the spatial resolution to look at every single axons, we have basically the spatial resolution to look at this bundle. And this is a reason why basically we want, basically we perform a diffusion MRI in order to be able to dissect and to look at basically this bundle, both in healthy and also in pathological condition like aging or brain development. Okay, so the basic of diffusion MRI is basically that we can differentiate between tissue in the brain based on how water molecules diffuse throughout the tissue. And this tissue is just basically a random motion of water molecules. So in basically in tissue, like in the gray matter, basically the diffusion is uniformly restricted in all possible direction. So the water molecule in gray matter are usually able to move in any of different direction, and that's why the diffusion in this part of the tissue is called isotropic. Instead, in the gray matter, which is actually what we are interested in with to measure with diffusion MRI, is basically in the diffusion in the white matter. The diffusion is preferentially restricted. It means that it is much easier for the water molecules to move parallel to the action rather than perpendicular to this action. And that's because basically the membrane of the axon, which is hard to permeate from the water molecules, and it's much easier for them to move in basically in a specific particular direction, which corresponds to the direction where the action is oriented. And in this specific tissue, in the white matter, the diffusion is called anisotropic. So basically with diffusion MRI, if we can figure out in which part of the brain basically the diffusion is anisotropic and in which part of the brain the diffusion is isotropic, we can tell whether there is a white matter or not. And this is basically and for basically any particular location in the white matter, we can figure out the preferential direction of the diffusion, basically the direction where the motor molecules are more basically likely to move. We can infer whether is basically the underlying orientation of the axon and the bundle. And that's why basically we perform what is called basically diffusion encoding. So basically we apply those diffusion gradients, and basically what we get at the end of the scan session, we get this 4D volume. And this 4D volume is made of a baseline image or images, depending on how many we are going to acquire, where basically no diffusion gradient were applied. And then we have the images where the diffusion encoding was applied. And these diffusion gradients were apply in different direction. And we will see why we basically apply this diffusion gradient in different direction later on. But for example, in this image right here, images right here, you can see an example of an image that was acquired with a diffusion gradient applying a specific direction, which are different from the images that I was telling you before, the baseline image, because they are much brighter. But anyway, this one, basically, the voxels that are shown here as darker are basically the location of the brain when there is a lot of diffusion in that particular direction, which we apply the diffusion encoding gradient to collect this image. And the part of the brain is, on the other hand, that are shown as brighter are the one where there is less diffusion of water molecule in that specific direction that we apply our diffusion gradient to. And that's basically also, this is for the image that we acquire, but basically also when we acquire a diffusion weighted image, we also will end up having a BVECT and BVEC file, which I'm going to show you in a minute. But basically, the B value file, it basically encodes what was the timing and the magnitude of the magnetic field that we apply to basically acquire our images. Whereas on the other hand, the B vector is going to be an array of X, Y, and Z direction, which correspond for basically is going to tell us for every images that you acquire what was the diffusion encoding direction of the gradient. And okay, and this is basically what basically is the diffusion images. For today, we are gonna work with a data set that is publicly available, and we are gonna basically fetch this data set using brain imaging data structure, or BITS, which I'm sure you are familiar at this point of the lecture. And so we can basically.
Davide, can you make the text a little bit bigger?
This one?
Yeah. Yeah, that's better.
Better?
Yeah.
Thank you, Erin. Yeah. Okay. So, yeah. Moving along, yeah, I would say that basically we are gonna work with this question, this data set, and the question is basically at this point might be why we need to acquire basically our data and encode our data with basically different gradient direction. Our choice is basically was made because when we collect our diffusion data, we are going to collect basically different images with different encoding. So this is because if you are basically really lucky and the diffusion, the true diffusion is basically, so the direction of the where the water molecules are moving to are diffusing is exactly parallel to how we apply our diffusion gradient, we are going to see a maximum changes, so a minimum drop in the signal in that specific voxel compared to the baseline image. So it turned out that in that specific case, we are able to detect basically the water molecule, the specific direction of where the water are moving to with really less error. But on the other hand, in the opposite scenario, when we are really unlucky, and let's say that we apply our diffusion gradient exactly perpendicular to how the water molecule are exactly moving, what we actually see in that case is not changed at all in the DWI signal, even though in the ground truth, so in the data set, there might be some changes that we are not able to detect. So that's why basically people in general acquire their image with different diffusion gradient in different direction. And basically the direction in to capture basically all the possibility in between of these two scenarios that I just illustrated to you. So, and the number basically of different gradients that we basically we collect our data to are basically the what is called the angular resolution, which is basically the smallest angle between the two axial bundles that we acquire. So coming back basically to our data set, so if you scroll down in this page, we should be able to see this source. So if you click on this, then you should be able to open the bits, the binder, as Erin was described before. And it might take a little bit, yeah. Let's see. Yeah, in the meantime, what we are going to do with this open data set. So this is actually the structure of the bits folder, which I mean you are familiar with at this point of the tutorial lesson. But basically, this is we are going to work with the anatomical folder for the for example, T1 weighted image, when basically we are going to register our dWi with the anatomical structural imaging. But then mainly we are going to work with this folder, which is the dWi. As you can see in this folder, there is an IFTI file, which is basically this for the image that I just described, made of basically the baseline imaging, the bit 0 images, and the diffusion weighted images. And then we have this bvect and bval file that I just described before. So let's see if it's, yeah, probably gonna start soon. All right, so let's start with the introduction. So this is basically what I was saying before. With bits, we can basically collect our data set. So in this case, we are going to work with this data and this specific subject folder. And with this line of code, we are basically going to grab the subject, the extension, so with the nifty file, the 4D file that I just described, and this is the name of the folder. I'm going to run this cell. So these are basically the information related to the scans acquisition. So for this tutorial, we are basically going to work with DIPy, which is an open dataset that allow us to basically pre-process and analyze diffusion weighted imaging. And is completely open dataset, is structured in Python. And I mean, it's we are gonna basically work with that for this tutorial. First of all, we are gonna also, together with the diffusion, basically the nifty file that we just grabbed from the folder, we are also gonna grab the bvec and bval file using this cell. So basically in DIPy, there is basically a function that allow us to basically group together this bvec and bval file in just one variable. And this is what we are gonna do later on. First of all, we are gonna basically, once we basically fetch this open data set, we are gonna load it the data that are stored in this nifty file using this nibabel function that I'm sure that you already encountered in the previous episode of this lecture. So, and we are gonna also print the shape of this 4D volume. So basically, as you can see, it's a 4D volume. The first three numbers are basically the dimension of the image over the X, Y, and Z direction. And the last one is basically how many images were in this data set. And as you can see, are 67. This is because basically we have 7 different B0 images, which are basically the baseline images where no basically gradients were applied to. And And then we have 60 diffusion weighted imaging where basically we apply a gradient in a specific direction. And in this cell right here, basically we are gonna plot one of these B value in this case, because as you can see, we select a specific location in the space, X1Z, and then we are gonna grab basically the first volume, which is this baseline image. And as you might see from this, and as I was saying before, this is actually brighter than the one that we basically seen right here. So those are basically the diffusion weighted images where we apply a gradient in any specific direction to encode our images. This is where basically no gradients direction were applied to, and this is the baseline image. And we have 7 of these in our data set, and we collect this during after, let's say, 8, 9 diffusion weighted image. There is a baseline image, and then so on and so forth until the end. So first of all, we also have these basically gradients, which are the B vector. So basically, these are the direction of the where basically the diffusion gradients were applied to encode our imaging and our images at any specific time. It turns out that we can plot basically those diffusion gradients direction in resembling like a sphere. And this is gonna be, let's keep this tab open later on, because this is actually one of the principles where to basically be able to reconstruct the fiber tractography, for example. And people came out with algorithm like spherical deconvolution that we will see later on in the tutorial to pass from basically a spherical representation of the diffusion weighted imaging signal to something that is more similar to a bundle, a Faber orientation. Anyway, moving along with this introduction part, we are gonna basically, as I was saying before, in DiPy, there is this gradient table where basically we are able to store and group together our B vector and B val in just one simple object like this one. So I'm gonna run this cell, and there is also a built function for inside this object, which is basically B0's mask, that is allow us to separate basically the baseline images from the diffusion weighted measurement. And this is actually what is gonna happen here. So as you can see, we basically extract only basically the direction of the diffusion gradients. And as you can see, we can also plot basically what is the extension of this file, and is 60. So as I was saying before, we are basically acquire 60 diffusion weighted image in a specific direction and 7 baseline imaging. And this is similar to what we were saying before. We can basically check where basically our B0 images are located in time. So basically those are 67, which corresponds to our images in the 4D file, nifty file. And where it's true means that a B0 image, a baseline image was acquired. And as you can see, there is something in the first one that we just plotted here, but there is also some baseline image in between. And this is actually important for registration and for motion correction. That's why also people acquire other baseline image in between. So moving along with this tutorial, I think that if there are no questions, we can move to the second part, which is basically the pre-processing step. And I think we are good because we will have a break coming up after this part. So let's move directly to the pre-processing step. So as you can see, this is actually an overview of an imaging of basically all the pre-processing steps that can be applied to the diffusion weighted imaging. And there is some consensus and some of the pre-processing step that instead depend on how you basically acquire your data. And today, basically, we are gonna really focus on specifically for the pre-processing to the top up and the eddy. But at the beginning, we are also gonna see basically how to extract a brain mask from the diffusion data, which is important for registration, for example. And as I was saying, at the last part, we are gonna basically register our diffusion weighted image and the anatomical image, which has basically a higher spatial resolution. So moving along with the tutorial, first of all, we are gonna basically extract, as I was saying, a brain mask from our data set. And the diffusion data set. This is actually, first of all, in this line, we have already seen some of this command. So this is actually what we have already seen. The only really new part is the last cell, where we basically also collect this T1 weighted image. As I was saying before, we are gonna also work with anatomical. So not really new in this cell. So in this cell, instead, we are basically gonna collect our nifty file using nibabel, and we are also going to collect the transformation matrix of this DWI image, and also, of course, the data set, the 4D data set. So basically, nothing really new also in this cell. And moving along, in this, basically, in the following cell is where basically we are going to extract our brain mask using basically this function media otsu, which allow us basically to segment and collect the brain mask. So first of all, we are gonna import this function from DyPy, and then we are basically gonna extract both the skull strip brain and the mask, and then we are gonna define the output director, and if basically the directory already exists, we are gonna create. Doesn't exist, we are gonna create a new one, and then we are going basically to define this nifty object using the mask that we are interested in saving, and basically with the affine transformation matrix that we just extracted from the cell before. And then finally, we are going basically to save our nibabel object, nifty object, to this location that we just defined. So yeah, something that is really simple, and okay, so now we can move directly to the first actual pre-processing step, which is top up. So it turns out that in the API, which is spine echo planar imaging, this is actually an artifact that is not only limited to the diffusion weighted imaging, but also to the fMRI, for example, if you are more familiar with. But basically, what happened is that the magnetic field that we apply for acquiring our images is basically as inhomogeneities. Okay, that's okay. I think, yeah. So basically, there is a signal loss in the interference between the tissue and, for example, the air, like we have in the sinus. So what is happened is basically that there is a stretching in the image that is highly dependent on the direction when we acquire our basically images to, and this is actually called a susceptibility artifact. So the bit 0 is basically the magnetic field, and basically we could have a bit 0 distortion in, for example, these frontal regions. And an example of this data set, I prepare an image just to show you, yeah, for example. Yeah, this is actually what is the common artifact. This is a bit 0 image. As you can see here, the direction of the encoding was to posterior anterior, and where basically there are the sinus, and in basically the space between the air and the sinus, there is basically this stretching in the image. Whereas if we apply, basically, if we collect the same image using another phase encoding direction from anterior to posterior, we have basically, we miss some part of the brain. So this is actually what susceptibility is, and this is what we are trying basically to correct for top up. And a way basically to correct for this artifact is to do it in the post-processing, so after we acquire our image. And in order to do that, either we acquire the field map, or what is actually more common, we can basically collect our images using two-phase encoding direction. So we can acquire a baseline image from anterior to posterior, and we get an artifact and a stretching in the image, and we can acquire a baseline image in the opposite phase encoding directions from posterior to anterior, and we can get basically the other artifact, as I show you in the slide. And if we basically feed the top-up algorithm with these two different encoding direction, we are able to correct for this artifact. And this is actually something that is implemented in FSL. So we are actually not gonna run this because we don't have a FSL installation on this binder, but just for the sake of tutorial, I'm gonna illustrate it how basically it works. So everything is in bash. So this is actually a bash command, not a Python. And we are gonna basically create this directory in this specific folder. And in order to perform the top-up algorithm, we need to create basically the acquisition phase encoding map. So we already have basically this file where basically the baseline image were acquired from anterior to posterior direction, and another one from posterior to anterior direction. We are gonna merge together these two images in this file, and we are gonna save it in this directory. Then, basically what we need to do, we need also to create a txt file, which basically is this pi.dir.txt file. This is really simple. It's basically gonna tell the top up and the algorithm what basically was the phase encoding direction of our baseline images. In this case, the key is basically this second number. As you can see, this basically tells us that the first images were acquired from anterior to posterior direction, and the second three images were acquired from posterior to anterior. So as you can see, the only number that's changed is the y direction. So we have already created this file in that folder. So we are ready to perform a top up, and it's another bash command. And basically the command is really simple. IMain basically is gonna tell us what is basically the bit0 images that we just created with the previous command and we merged together. The pi.dir.txt file is gonna be here in the --data_in, and we just created as I described 2 minutes before. And then it's gonna output basically our folder in this location. And after we basically, this is gonna basically estimate only the distortion of the magnetic fields. After we estimate the distortion on the magnetic field, we just apply it to all the basically the DWI images and our 4D nifty volume. And this is what actually is gonna happen in this cell. So it's another bash command. It comes from FSL. We apply the top up basically to our 4D volume using basically the diffusion encoding information that we just created. And we are gonna basically inform the algorithm what is basically the distortion that we just estimated before, and is gonna output basically the corrected image in this specific folder. And exactly this is gonna happen. I just wanna show you what is basically the result. Yeah. So this is actually the result after we apply the top up. As you can see here, there were some missing part of the brain. After we apply this correction, it much more, I mean, reasonable in terms of brain geometry and etc. And after this, we have another basically pre-processing step, which is heady. So heady is basically really specific to actually the DWI and depend on basically the b-value, and it works when the b-values are higher, and depends on basically the gradient direction, and is a distortion that is dependent on the switch between the gradients. And basically there is another FSL commands that allow us to correct for basically this distortion, and is called heady. And basically we are not gonna run this, but because it takes actually a long time, but I can show you basically what is the command and what is the output. So first of all, is another bash command. We are gonna create this directory in order to store our output. So in this cell right here, this is actually a for loop to create what is a index file. So this index file is basically a file, a txt file, where there are, for example, in our case, 67 value, because we have 67 volumes. And for every volumes, it is gonna basically tell us what was the intensity of the magnetic fields to acquire that volume. For example, for the baseline image, is gonna be 0, right? But for the other diffusion weighted image with different encoding, it might be different depending on the acquisition that we have used. In our case, it's standard because our acquisition is a single shell. So in our case, the strength of the magnetic fields is 1000, and is constant for every diffusion weighted image that were acquired for different encoding. But there are other, for example, let's say if we are interested especially to investigate the microstructure of the white matter, such as the diameter of the fiber, such really specific fancy stuff, people start basically to acquire the data with different magnetic fields magnitude, and this is actually going to increase the spatial resolution, but we don't have in this data set because I was saying a single shell. But this is what basically this for loop is going to be. It's going to basically create index file, .txt file with 70s entry, and it's going to be basically a bunch of ones, because basically our magnetic fields is constant over all the acquisition, so it's not going to change. And finally, we are able to perform this eddy correction. So basically the flag are, the input is going to be our diffusion weighted nifty file, the mask that we just created in the previous tutorial in this location, this acquisition parameter, which is basically the PADR txt file that we used it before for the top up, this index file with basically a bunch of 0 and 1, depending on if you acquire, if our image is a B value or a diffusion weighted image, and our B-vector and B-val, and basically it's gonna output out the top-up information on the distortion of the magnetic fields and our output. So I can actually, I think I can show you directly what is the main output of this. So it's gonna be on derivative, and let me see, top-up eddy. Yeah, so this is actually what an output look like. So we have basically our dwi.nifty file, which is basically the DWI corrected for eddy distortion. And more importantly, we have also this rotated BVEX. So this is actually a file that is similar to the original BVEX file. So it's basically contain the direction of the gradients that we apply to correct our diffusion weighted image, but is correct for the motion. So for example, let's say that we acquire our image with a gradient apply in this direction. So what happens if basically the subject is moved during our session? and we keep to basically keep the same gradient orientation, we are not basically gonna be accurate. We need basically to account for the motion and also rotate the gradients. So this is actually what is going on in this file right here. And this is actually the output of the EDDI. Last pre-processing step, which is actually not really a pre-processing step, but basically we are gonna register the dWi and the anatomical together. And for this, we are gonna use another tool, which is ANS, and this is actually really useful for registration. First of all, we are going actually to extract basically a brain mask from the our anatomical image. And for this, we are gonna use another FSL command, which is BET, brain extraction tool. And this is what happened in this cell here. We are gonna basically create an anatomical folder. Then we are basically applying BET one time using this threshold. And then we apply BET another time using another threshold to just refine basically the outline a little bit. And we are gonna output with this flag -m the mask in this location right here. And then with this last command, we are just move basically the mask. We are just renaming actually. We rename the mask with underscore to without underscore and in this location. So after we actually perform this brain extraction tool, we are basically gonna use Medianotsu again to extract basically the brain mask from the dWi. So this is actually something that we already seen in the previous tutorial. We are gonna save this dWi mask in the EDDI basically folder. So using the corrected folder, the corrected data set, and we are gonna basically save both the B0 volume and the 4D volume in this location. And after we perform this basically preparation, we are actually able to use ANS for registration, as I was saying before. So it's gonna be another bash command. We are going to basically create this directory for transformation. First of all, we are gonna basically compute the transformation matrix, and specifically we are gonna compute the transformation matrix between the B0 and the structural, and then using this command. So it's actually really simple, where basically the -f it means the reference image, which is the this brain extracted structural anatomical image, and the moving image is gonna be our B0, and this is gonna be the transformation matrix. So after we create the transformation matrix, we apply basically the inverse using this apply ANS apply transform to the dWi with a similar command. So basically in this case, we are gonna apply our transformation matrix to all the 4D volume. So and the register image are gonna be in this output direction the folder right here, and then basically this was the last pre-processing step, with basically as you will see, brain extraction tool, top up, FSL EDDI registration, and then we are basically ready to move to more fancy analysis. So I think we, as at the program, we should have a break at this point, right? After, if I'm correct. So if it's okay, we can come back like in 15 minutes, how it sounds like. If you don't have any question as well.
I think 15-minute break is fine.
All right. So I'll see you, I guess, in a bit.
Yes, let's come back at noon.
Sounds good.
Davide, I guess we can resume now. Please.
Sorry, say again.
We could resume now if you're ready.
Oh, can we move forward? Okay, sure. Yeah. Yeah, let me actually, okay. Can you see my screen?
Yes.
Okay. Can you see the code and stuff, right? Okay. So, yeah. Moving along with we already seen the pre-processing. So, all right. So, basically, after we pre-process basically our DWI image, we want to know with the diffusion MRI if a specific voxel in the white matter is white matter or gray matter, and if basically the diffusion is anisotropic or isotropic. So, which basically we want to know where basically are the direction of the fiber and where basically the fiber are mainly oriented. And that's why we actually collect a 4D volume. And the information that we have is something completely different, for example, from a T1-weighted image, an anatomical image, when we have just, one volume and one interpretation. So what this basically slide is showing to you is actually not all, but is not an extensive overview of the main algorithm that came out in the last 20-25 years in order to figure out and basically to map the main direction of the diffusion in every specific voxel in the brain. And what we are gonna basically see in our tutorial, we are gonna first of all speak a little bit about the diffusion tensor imaging, which is the simpler model, but not simple. And then we are also gonna see the constrained spherical deconvolution and the ODF a little bit. Just to quickly move to the next part, basically the algorithm that we are going to employ in your data is highly dependent on how you acquire the data. For example, if you have a single or a multi-shell, and also, of course, depends on the scientific question that you might want to investigate. So, moving with the tutorial, I already opened the binder. Hopefully it's not gonna crash this time, but basically the diffusion tensor imaging, the DTI model. So the DTI model is based on actually a classical experiment, which is basically a pulse gradient spin echo experiment from the 60s, from Skistal and Tanner. That actually equation was in 1D, but basically what you can see in this representation is a 3D basically equation on the classical 1D Skinner and Tanner model. And it's basically tell us that the strength of the magnetic fields, so basically the signal changes is function of different parameters. And these parameters have been actually encoded in this B variable from, for example, specifically Lebihan. And basically what this equation is saying is that basically this 3x3 matrix or tensor D is kind of basically mapped into this B vector. So, and is dependent of the direction of this theta. And we can, for example, normalize the equation for the B value. And we can also take the logarithm of both sides of this equation, and this turns to be basically a linear equation at the end. But basically, what is this D vector? This is a tensor or a 3x3 matrix. And is basically also a rank 3 matrix. And what basically is encoded in this matrix is for every voxel, it tells us basically the direction of the diffusion. And is basically the information that we have in this matrix is encoded the variance of and the covariance. the variance, of course, in the diagonal and the covariance of the off diagonal of this matrix of the diffusion in a set of axes. And it turns out to be a symmetrical matrices. So basically the covariance, for example, of x and z is equal to the covariance of z and x. So that's why actually we need a minimum of 6 direction of each voxel for basically perform a diffusion tensor imaging model, because we only need, 6 of these numbers. And if basically we are, we can take what it turns now that we can basically extract and perform a eigen decomposition of this tensor of this 3x3 matrix, and basically this is something that is called positive definite, and this is actually allow us to describe all the tensor in terms of 3 eigenvector and 3 eigenvalue. And basically the physical interpretation of this is that the eigenvector express basically the direction in which the diffusion is going to be in a specific voxel, and the eigenvalue instead express how much diffusion is happening in each direction. So, for example, in voxel of the brain, when we have, for example, isotropic diffusion, like in the ventricle, let's say, then the 3 eigenvalues, sorry, are gonna be really similar each other, and the tensor is gonna be looking like symmetric and like a sphere. Okay, so on the other hand, in part of the brain, when we have a single bundle that is going to be there, for example, in the corpus callosum, and so it's gonna be in that specific voxel much easier for the water molecule to move in a one specific direction, let's say from left to right, if you look at the splenium, then there is going to be in that specific voxel that one of these eigenvalue will be much greater of the other two, right? And that is going to be the eigenvalue, which corresponds to the eigenvector that is aligned preferentially to the direction of the diffusion. So that tensor in that voxel is going to be elongating along the direction of the diffusion. And this is actually what is shown in this specific graphical graph. So for example, in this case, this first eigenvalue is much greater than the other, which means that the diffusion is going to happen in this direction, right? So, so basically what we are going to do, we are going to perform this diffusion tensor imaging model in dipy. So moving along directly to the code part and with the tutorial, basically in this cell is actually something that we already seen it. So basically we are gonna just collect importing basically the module and the function that we need from dipy, choosing the data set and collecting the DWI, BVEC, and BVAL, and then collecting the data and the DWI data and the T1 weighted data, and storing basically the BVEC and BVAL in this GTAB. So nothing really new is happening in this cell. We already have seen it. Then this is also something that we already seen it before. So basically we are creating a mask for the diffusion weighted image we are gonna basically store this in these two variables. And then what we are gonna do, we are gonna perform the diffusion tensor imaging model in these two lines. So as you can see, it's really handy and simple in dipy. All this equation and stuff that I explained you at the beginning of this tutorial is gonna happen literally in 2 lines of code. So here we're basically gonna call the diffusion tensor model, and then we are gonna fit it to our data using the mask that we extracted and the DWI for the volume. So I'm gonna run this cell, and probably, yeah. Let me see if it's okay. In the meantime, we can move basically to the explanation. Basically, after, as I was saying, after we perform this eigenvector decomposition of the diffusion tensor, we will get eigenvector and eigenvalue for every voxel in the brain. Basically, there are different ways that with this eigenvalue can be combined together in order to get basically a map of the diffusion of the water molecule displacement in each voxel, right? So the more standard way, basically, to one of these is basically the functional anisotropy. The most common one are actually the functional anisotropy and the mean diffusivity, and then we are also going to see axial and radial diffusivity. So for functional anisotropy, basically tells us something on how different the three eigenvalues are from each other in any particular voxel. So it's basically gonna store the variance of the three eigenvalue, normalized, as you can see, by the sum of the square, and afterwards is gonna be basically a map with value that range between 0 and 1. So in part of the brain, when we have isotropic diffusion, like ventricles, so basically lambda 1, lambda 2, and lambda 3 are gonna be really similar each other, so that their functional anisotropy is gonna be 0, and gray matter is gonna be darker, for example. On the other hand, in part of the white matter, when we have highly anisotropic diffusion, for example, the splenium of corpus callosum, when the diffusion is going to be from left to right, then lambda 1 is going to be greater in the corpus callosum than the other two, lambda 2 and lambda 3, for example, and the FA in that case is going to be closer to 1, okay? So this is actually, we can basically extract this map directly from we already basically have this map because are storing this DTI underscore fit variable that we just created by fitting the tensor model to our data. So here, what we are gonna do, we are basically gonna extract from this basically TWI fit, the FA, the functional anisotropy image, and we are gonna store it in a nifty volume, and then we are gonna plot it basically. And we are gonna plot this X, Y, and Z coordinate. And yeah, as you can see, as I described before, in this, for example, region of the brain, the splenium, where the diffusion is gonna be from left to right, we have higher basically functional anisotropy value. So this is gonna basically be informative of what is the main direction, what are the covariants between the eigenvalues between each other. And it's actually a useful measure for example, investigating the white matter degradation or for some pathologies condition. And there are, I mean, multiple studies in that field. And it's the most used actually map that we can get from the diffusion tensor imaging. Another one that is actually really employed is the mean diffusivity, which is basically, it's really simple, is the mean of the three eigenvalue at one particular voxels. And basically it gives us a metric of how far the water molecule can move. And for example, in the CSF where there are no barriers and the MD is gonna be higher, so the MD map is gonna be brighter in that part, while inside of the brain, for example, where there are more barriers and the water molecule are not able to go too far, the MD in that part is gonna be lower. And so similarly to what we already done for the previous cell, as I was saying, this object we already have all what we need. So this time we are gonna collect the mean diffusivity map, and we are gonna store it in this variable, and we are gonna plot the same exact basically image and the same exact location. And yeah, as you can see, where in the part of the brain, like in the ventricles, there is no diffusion. The MD image is going to be brighter compared to other regions when there is, for example, diffusion in a particular direction. So moving along, there are basically a couple of other measures that in general are used in literature. So first of all, the axial diffusivity. The axial diffusivity basically corresponds to the greatest of the three eigenvectors, so the lambda 1 in every particular voxel. And these measures basically reflect, as you might have noticed, how far the water molecules are moving to the direction that is parallel to the white matter bundle, right? Whereas the other measure, the radial diffusivity, is the average of the other two eigenvalues, so lambda 2 and lambda 3, which represent how much diffusion is perpendicular to the axon bundle, and this actually come from the name. So axial diffusivity, diffusion parallel to the axial bundle, radial perpendicular, okay? And there are basically some interesting statistical measures that we can extract from all these measures. And it's actually, there is one statistical pipeline that is highly used, for example, is TBSS, track-based spatial statistics, that come from the FSL group, when you can basically, it's a way that, let's say you have two samples, one healthy and one sample of pathological people, you can basically statistically compare any of those maps that I just described in order to figure out in which part of the brain, for example, there is less functional anisotropy in the pathological group compared to the healthy, and so on and so forth. But just to say that there are basically some interesting properties in this map. So moving along with the tutorial, before jumping to the next question and the next model, I just wanna say that, for example, there are this diffusion tensor imaging model is actually useful for visualizing how basically what is the main direction of the diffusion in any particular voxel. And for example, you might have seen this for also in 3D. And this is actually, I think, the most beautiful image that you can get outside from DTI. So basically, this image is telling you what is the main direction of the diffusion. For example, the blue color, it means that the diffusion is going to be from superior to inferior direction. Whereas, for example, for the red, it means that basically the diffusion is mainly going to be from left to right. And for basically green is going to be anterior posterior. So with one simple image, you can basically try to figure out what is going on in every voxel and what is the main direction of the diffusion in any specific direction. However, what we have seen so far, basically, this is going to be all right and it's going to be fine. For example, if we have one single bundle, let's say in this plane of corpo calloso, the main direction of the fiber are oriented from left to right, right? So in that specific voxel, our model, the TI model, is going to be, of course, perfect. But if we have, for example, a situation like, for example, in this part of the brain, where basically the fiber are not oriented in any specific direction, but we have a situation when there are bundles that are crossing each other or are kissing each other. So the tensor in that case, in this case, is not going to be a good model, like, because basically what is going to be is going to average in all possible directions. And in that case, you might end up with a map that say that there is no diffusion at all in that specific voxel, but it's not just because there is no diffusion at all, but just because the model is basically averaging the two opposite directions where the diffusion is actually moving, right? So that's why people are actually going to move to other, for example, model, which is going to be basically the constrained spherical deconvolution, for example, and is going to be the topic of the next tutorial. First of all, we are going basically to see this exercise. We are just gonna probably run it and explain a little bit what's going on, but I'm sure you already know. It's not really something new. It's basically we are collecting all the images that we need from the same directory. So it's kind of a summary. We are gonna store the bvect and bval in this gtab, collecting the data and performing a brain mask extraction, running the diffusion tensor model, fit the diffusion tensor model to our DWI data using the mask, and then basically what we are going to see, we are going to extract the axial diffusivity and radial diffusivity. So it's the same basically stuff that we did before here for the MD and for the FA right here, but for the last two map that I just described. So if we don't have any question, I can, yeah, and this is basically how the plots look like for axial diffusivity and radial diffusivity in the same voxel XYZ coordinate than before. So if there are no questions, I can directly move to the last part of what I'm going to present, because then Brad basically is taking over this tutorial right at the section 2. But basically, this is something that I just described before, partially is basically related to the fact that in basically part of the brain, when there are situations when there are crossing fiber and kissing fiber, or basically the direction is not going to be in just one direction, like in the splenium, we need some more sophisticated, let's say, model. And this is something that is, for example, spherical deconvolution is trying to solve. So basically, spherical deconvolution, we have our DWI signal, and a good say that if you have like our DWI signal and we have a good approximation of what our response function is gonna be in all the voxel, we can assume that, which actually we can assume that is equal for all the fiber population, and is actually one of the biggest assumptions of spherical deconvolution. If we have these two information, we can recover the fiber orientation distribution function. This is what the constraint the Fourier convolution is going to be. And in order to perform this spherical deconvolution, we need to know what a spherical harmonics is. So basically, spherical harmonics are basic function or for any spherical function on a sphere. So just like sine and cosine for the Fourier transport, in imaging, basically spherical harmonics are basically Fourier transform on a sphere. And if they are basis, it means that we can basically reconstruct any spherical function on a sphere just with a series of spherical harmonic coefficient. And so basically, given any spherical function, we can express is basically as a linear combination of a little bit of a sphere, a little bit basically of spherical harmonics, and so on and so forth. And we can reconstruct this crossing fiber using a model that is basically a combination of different spherical harmonics. And this is actually what this function is going to tell us. So basically, we have a sphere, which is going to be our DWI signal, where basically every radius is a direction with a certain value, which corresponds to the gradient. And this is going to be basically a spherical function. So DWI for every particular direction. And we can project this into a spherical harmonic basis, as I was saying. And the way to do this is basically implement this Fourier transform on a sphere. And this given, so basically this is basically the equation. So a signal on a sphere, which is basically this term right here. And if we have our basis, which is basically this here, is sole matter of, we have to find these coefficients, right? And basically, this is what spherical deconvolution is to find the spherical harmonic coefficients for our diffusion weighted signal. And in dipy, this basically basis element are called a spherical harmonic matrix. And it turns out that the implementation in dipy is going to be really simple. If we give us dipy, basically, if we give dipy this spherical harmonic matrix, it return this seed, so the coefficients of the spherical harmonics. And in the algorithm, there is also a small regularization going on, but basically dipy will fill dipy with this matrix, and it's going to basically implement a least square, or actually a pseudo-inverse spherical harmonic transport to provide basically these coefficients here that we need in order to reconstruct our signal. So I'm moving along basically with the tutorial. I'm gonna simply run this cell because this is actually that we already seen it in the previous tutorial. So first of all, as I was saying, we are gonna basically estimate the response function for our data set, which the spherical Boole convolution is actually assumed that is constant for every fiber, for every voxel in the brain, and is actually one of the biggest assumptions. And we are gonna basically estimate the response function using this dipy function that we just imported. And we are gonna save it as a txt basically in this location that we just specify right here. So basically the response function contains two elements. The first is an array with the eigenvector of the response function, and the second is the average S0 signal value for this response. So we can actually plot it and plot this number of the response function that we just computed, and the tensor generated belong to response function basically, and is basically we can plot it also the ratio, and in order to basically before perform the actually computation of the coefficient is actually a good practice to plot and visualize the response function that we just estimated, just to see that it looks reasonable. And I think the visualization, is actually this cell right here is not working on the binder, so I can actually show you directly in this website location. Yeah. So yeah, this is actually an estimation of basically the response function. And this response function should basically be anisotropic and indicate basically the direction of the diffusion in a specific direction. So if you don't have any question, I can, leave the floor to Brad, which is actually taking over the rest part of the tutorial. And
Cool. All right. Well, yeah, thanks for the intro, Davide, for the rest of the diffusion. And I'm going to take over just the last bit of the constrained spherical deconvolution, and then we're going to talk about some tractography, and then hopefully we'll end off at probabilistic tractography. So after I'm done this second part of CSD, we're going to have a quick 10 or 15 minute break, and then we'll get into some tractography. So let me just hide this video panel. Okay. So we're going to talk about how to actually reconstruct this fiber orientation distribution function. So as Davide talked about, once we estimate this response function, this idealized signal of a single coherent bundle in a single voxel, so the response function, we can construct the fiber ODF through what's called deconvolution, which is a mathematical operation that we won't go too much into. We'll focus more on the practicality of it. But essentially, we obtain the spherical representation of the diffusion signal. And we do this by specifying an order of the spherical harmonic expansion. And so this order corresponds to an angular frequency of the basis function here. And so the spherical harmonic expansion, it's infinite. So we need to truncate it to a certain order to actually model the diffusion signal. And so the maximum order we specify will determine the number of spherical harmonic coefficients we have to use to represent the diffusion signal. So it's important to note that the number of diffusion encoding gradient directions needs to be at least as large as the number of coefficients. So the maximum order, L max, is determined by the following equation. So where R in this equation is the number of coefficients we're going to use. So for example, with an order L max of 4, 6, and 8 respectively, the spherical harmonic series has coefficients 15, 28, and 45. And so note that the use of even orders here. So even orders in spherical harmonic space essentially reconstructs a symmetrical spherical function. And we do this because it's motivated by the fact that the diffusion process is symmetric around the origin. So we want to reconstruct a symmetric spherical function because of the diffusion process and its symmetry. So we use even orders here, 4, 6, and 8, for example. So in this code cell, we're showing you how to actually perform constrained spherical deconvolution in DiPi by calling the fit method of CSD. So we import our reconstruction CSD deconv model. We specify the order we want. So in this case, our order is 8. So we're going to have to save 45 spherical harmonic coefficients. And then we initiate our model similar to what we've seen before. We give it our gradient table. We give it the response function we just calculated, and then the order that we specified here, which is 8. So here we're only going to fit just a small portion of the data, so a small slice as seen here. And that's through the splenium of the corpus callosum. So we fit our model using .fit to our data that we just specified, data small. And then we can get our spherical harmonic coefficients from this fit. So that's getting obtained here. So dot spherical harmonic coefficient. So that little piece of code there is extracting those spherical harmonic coefficients at every voxel in the data we specified. And then we can save those to an image. We can save those coefficients to a Nifty file. So we have the coefficients. Now we want the FODFs. And so this is pretty straightforward in DiPi as well. One important side note, though, is that the distribution recovered from spherical deconvolution, the FODF, is different from what's called the DODF, or the diffusion ODF. So the diffusion ODF is more driven just by the raw data. So we don't use a response function. You essentially just use what's called the Funk-Radon transform, and it's just from the raw diffusion signal. And the diffusion ODF is much clunkier or bigger than the FODF. The FODF tends to be a lot more sharp, although they contain or convey the same information, the direction of diffusion or the direction of the fibers. It essentially contains the same information. One is just sharper than the other. So to actually get our FODF, we have to put our spherical harmonics onto a sphere. We need to expand those and actually put it on a sphere. So that's what we're doing here. We're defining just a default sphere to essentially put our ODF onto. So we can use the generate anatomical slice figure. So this function that will just allow us to generate some anatomical views. And we're going to look at the central slices of this region that have been used. So we make our actor to visualize the scene. We put our ODF in that actor, the sphere that we use, the default sphere, and then a bunch of other parameters such as the color map and the scale. And then just the rest of this code is just essentially generating this image. And so here you can see the axial, sagittal, and coronal slices of the FODF. So for example, here you can clearly see the lateral ventricles here, and also the corpus callosum. And if I can zoom in just a little bit, see if that works. Okay. Oh, it didn't really zoom that in. Essentially, you can just see the highly coherent oriented region of the corpus callosum. So you can see that the FODFs have one main direction because the corpus callosum is a highly coherent bundle. Oops. Just zoom back out. Okay. So an important thing that we can do as well is take the peak directions from the FODFs. So this is typically what a tractography algorithm will take in. It will take in the peak directions. We don't need to feed it the whole sphere. We just want to feed it a vector that is pointing in the direction of the main peaks. And so DiPi offers the peaks from model method here. So we import our two modules that we need. So DiPi.direction and DiPi.io.peaks, and we import the peaks from model and then the reshape peaks for visualization function. To get the peaks from the model, we feed it the model that we use, so constrained spherical deconvolution, our data, the sphere that we're going to use, or that we use, the default sphere, and then the relative peak threshold, which we set at 0.5. And this essentially tells us how big does a peak on the sphere have to be for us to consider it a peak, right? So it has to have a threshold, a peak threshold of 0.5, and it has to have a minimum separation angle of 25 degrees. So to be considered a peak, it has to be 25 degrees away from any other peak. And then we can save this vector file, this peaks nifty, and then we can also save its indices, so where these peaks actually are on the sphere. And again, we do a similar visualization. We set up our actor, and then we give it our peaks and our peak directions and our peak values. And so here you can see the actual vectors now of those main peaks. So again, in the corpus callosum, you can see we have one very coherently oriented structure. So we have these vectors pointing in one direction in this corpus callosum region. So that's one peak. But if we look over here in this coronal slice, you can see that we actually have two vectors that cross each other. And that's just representing that there's two peaks now on the FODF in this region. So that means that's telling us that there's crossing fibers in this region, or the diffusion signal was attenuated maximally in both of these two directions in the raw signal, suggesting that there's two fiber bundles here. And then finally, this last bit of code is just visualizing both the FODFs and peaks in the same space. So right underneath, for example, again, in the corpus callosum, you can kind of see the FODFs and you can see those peaks, the peak vectors overlaid on top. And again, it's a little hard to see here. The FODFs are kind of small, but essentially you would see an FODF, for example, in this voxel that looks like an X. So it looked like an X representing two crossing fibers. So we're going to take, if there's no questions, we're going to take a quick 15-minute break. So we'll reconvene at about like 12:52-ish, and then we'll go over some tractography techniques if there's no questions. Okay. So I think we can get started again, and we're going to go over some tractography techniques, and hopefully we can wrap this up by 1:30-ish. Okay. So tractography. Essentially what tractography is trying to do is to connect the local fiber orientation from each voxel. So we try to reconstruct the voxel-wise fiber orientations and map that to some white matter long-range structural connectivity. So we try to study how the local orientations at each voxel, like we saw with the FODF and the peaks and also DTI, how we can integrate those to provide an estimation of white matter fibers which connect two regions. So tractography models axonal trajectories as geometrical entities called streamlines from the local direction information. And tractography essentially uses an integral equation, and it solves a set of discrete local directions which finds the curve or the streamline that joins them. And so the streamlines generated by tractography and also any metadata are saved into files called tractograms. And so the main family of tractography methods are local tractography, global tracking, what's called particle filtering tractography, and parallel transport tractography. So with local tractography, the main approach is to create streamlines from the local direction information. And the idea is that if the local directionality of a tractor path is known, we can integrate along these directions to build the complete representation of that structure. And that's mainly what we're going to go into today is local tractography techniques. Global tractography is the process of finding the full track configuration that best describes the measured data. And as opposed to streamlined tractography, global tractography tries to find a global optimum all at the same time. And it has some advantages over local tractography, and maybe we can get into that in a little bit. Finally, particle filtering tractography uses what's called tissue partial voluming. So at the resolution of an MRI or diffusion MRI image, you can typically get a blurring of the boundaries between tissues. For example, between white matter and gray matter, there's going to be voxels at the border between those two, where voxel will contain white matter and gray matter tissue inherently just by the size of the voxel. And that's called partial voluming. So particle filtering tractography uses that partial volume map to try and reconstruct trajectories that connect the gray matter and they don't prematurely stop in the white matter or CSF. So local tractography and particle filtering tractography can be separated into two approaches. So there's the deterministic and the probabilistic approaches. The deterministic approach essentially propagates streamlines using the same propagation direction. So if I ran a deterministic algorithm twice with the same set of parameters, it would give me the same set of streamlines back. Thus, it's a deterministic process. The result does not change if the starting condition is the same. Probabilistic tractography, however, uses a distribution function and it samples from that to decide on the next propagation direction at each step. So a pro of deterministic tractography is it tends to be faster and more simple. However, it's vulnerable to local noise at each voxel. Probabilistic tractography tries to deal with this by assuming that uncertainty in our direction measurement exists. And so we sample around a distribution of that direction. So it assumes that there's some uncertainty in our measure. There's a few cons of probabilistic tractography that global tracking tries to solve. So in probabilistic tractography, it has something called the index of connectivity, and that actually decreases with distance from a seed point. So from a point where we're going to start trying to track our streamline. So you're less likely to get streamlines that travel a long distance with probabilistic tractography. And that's a problem because we know there can be very large white matter tracts in the brain. And it's still somewhat sensitive to local noise. And that's partly what global tracking tries to solve by finding a global optimum at the same time. So it's less sensitive to these the long range bias essentially that we see in probabilistic tractography. So there's many algorithms to perform local tracking depending on the local orientation construct you used or the order of integration being performed. So some popular models are what's called fiber assignment by continuous tracking, or FACT, EUDX, which we're going to be using today and is commonly implemented in DIPI, and that's a deterministic method. IFOD1, IFOD2, and SD stream are just some of the algorithms that exist to actually propagate the streamlines. And there's further strategies to reduce the uncertainty on the tracking results, which have also been proposed. And if you're interested in further tractography, I suggest you look at some of these methods as well and try and decide what might be best for your data or your personal situation. It's important to note that tractography does suffer from a number of known biases and limitations, which can yield tractograms that contain a large number of prematurely stopped streamlines and invalid connections, or connections that we know should not exist. So there's a hard trade-off in tractography between sensitivity, so actually finding streamlines that exist anatomically, and specificity, so not getting erroneous streamlines or connecting two regions that we know should not have a connection. And so there's many enhancements that can be done to try and reduce those effects based on, one example is using some a priori knowledge, so anatomically constrained tractography, where you use anatomical knowledge to constrain your tracking. Structured tensor informed fiber tractography and surface enhanced tractography are just some of a few. And there's also been many deep learning methods that have been proposed to map that local orientation reconstruction to long range white matter connectivity. So that's the general basis of tractography as a whole. And so we're gonna mainly talk about local tractography. Local tractography follows two general principles. So it wants to, one, estimate the fiber orientation like we saw previously in our previous modules. And it's gonna follow these orientations to generate or propagate that streamline. And so streamline propagation is in essence a numerical analysis integration problem, and we need to find a curve that joins the set of discrete local directions. And so it takes the form of a differential equation problem of this form seen here. And we won't go too much into the actual math of propagation, but essentially we need to solve for the curve that will actually connect these points. So along with deciding on the algorithm you want to use to actually propagate your streamlines, you need to define three other things to your tractography algorithm. It needs to have a method for getting those local orientation directions from diffusion MRI. For example, we saw the tensor and we also saw the fiber orientation distribution function. So those are two methods that we can use to get the orientation that we need to use to track. A set of seeds from which to begin tracking, so voxels or masked regions that we're going to begin propagating from. And then we need to identify when it should stop tracking. So what kind of criteria do we want to decide when we should stop tracking a streamline? And so when further context data, for example, information on tissues such as white matter, gray matter, and cerebrospinal fluid, CSF, is added to the above process, the tracking is considered to fall into anatomically constrained tractography. So we're going to branch into the two main methods of local tractography, deterministic tractography, and then next we're going to do probabilistic tractography. So deterministic tractography, they track streamlines by following a predictable path. Like I mentioned previously, if you use the same set of starting conditions, you're going to get the same set of tracks. So it's a known deterministic process. And here we're going to show you how to actually perform deterministic tracking with diffusion MRI. So we've seen this before. We're just loading in, for example, we're loading in our B values and B vectors. We're putting them into a gradient table. We're loading in our diffusion image and our affine transform, essentially just defining the space that we're using here. And now we're going to create a mask, and we're going to constrain our fitting within that mask. So we're using, again, the median Otsu method that Davide talked about previously. And we're going to fit it to a tensor model. So we're going to run deterministic tractography on the tensor model. And so that's what we're doing here. And we've seen that previously as well. We set up our model and then we fit our data to the model. And we're going to use the EUDX algorithm, which is deterministic. And it makes use of the primary direction of the diffusion tensor to propagate streamlines from voxel to voxel and a stopping criterion from the fractional anisotropy measure. So we need, from the diffusion tensor model, we need our fractional anisotropy map, and we need our eigenvectors from our tensor fitting. So in the background of the FA map, the fitting may not be accurate as all the measured signal is primarily noise, and it's possible that we even have NaN or not a number values in the FA map. So we need to remove these so our fiber tracking algorithm doesn't get confused because it doesn't really know how to deal with not a number. And so we use these, we can remove these using NumPy, and we find and set these voxels to 0. So here we're collecting our FA image and saving it to a variable called FA image. We're getting our evex. And then we're going to set within our FA image, we're going to look for any not a number, any voxels that do not have a number, and we're going to set that equal to 0. And then we can save our FA image here, and then we can plot it. And so this should look like the image we saw previously in the diffusion tensor section. FA is really high in the white matter, and it's really low in the CSF, and also relatively low in the gray matter. And so one of the inputs of our UDX algorithm is the discretized voxel directions on a unit sphere. So we need to put those eigenvectors that we have, and remember, the eigenvector just shows us the main direction of diffusion, right? The eigenvectors, or DTI in general, cannot give us crossing fibers. So it just gives us the main direction of diffusion, or a single, essentially a single fiber population, a single coherently oriented fiber population. But we need to put that eigenvector, that direction, onto a sphere to be able to feed it to the UDX algorithm. So in this case, we're going to use a evenly distributed sphere that contains 362 points all around that sphere. And we can do this by using the getSphere function. So we obtain our symmetric 362 sphere. And now we're going to determine the indices which represent the directions of the peaks of the DTI model. So the peaks of the eigenvectors. So we need to set the minimum angle between the directions, the maximum number of peaks to return. In this case, the tensor will only have one peak because it only tells us one direction, and the relative peak threshold. So we're getting our peak indices here, the peaks from the DTI model. We tell it, here's our DTI model. We give it our data. We give it the sphere we set up. So we're projecting this onto a symmetric 362 sphere, and then we're getting the indices of the peaks once we get it onto that sphere. We're setting the threshold to 0.2. So it's going to return peaks greater than 0.2. It has to be at least 25 degrees apart. And we're going to do this within this mask. And we need to now specify a stopping criterion for our tracking. And that's typically done on the fractional anisotropy map. So we're going to stop our tracking when we reach a voxel where FA is below 0.2. So typically, your tracking is going to continue in the white matter where FA is really high. Anisotropy is really high in the white matter. And that will stop once you reach gray matter or CSF, for example. And that's typically because the FA in gray matter drops below 0.2 usually. So we can use the thresholding stopping criterion function. We give it our FA image and we say 0.2. So now it's going to make a mask that will essentially binarize anything above 0.2 and anything below 0.2. And so when our tracking algorithm keeps moving, if it reaches a voxel where FA is below 0.2, it'll say stop the streamline here. And then finally, we need to specify where do we want to actually begin the fiber tracking. So generally you choose the seeds depending on the pathway that you're actually interested in studying. So if you're interested in a particular region, you're going to want to seed in that particular region. So here we're going to create a seed mask from the FA map, and we're going to threshold above our stopping criterion. So in this case, we copy our FA image, and then we set any FA value above or equal to 0.2 as 1. So we're binarizing this seed mask. So anything above 0.2 gets a 1, and anything below 0.2 gets a 0. And essentially, that's going to give us the highly coherent white matter bundles back, and we're going to track or seed there. We're going to seed in these very coherent bundles, and we're going to stop tracking once we reach a low FA value. And so we set up our seeds from this mask. So we give it the seed mask, the binarized 1 and 0, representing regions of high and low anisotropy, the affine, so we're just defining the space that we're doing this in, and then the density. So this is essentially how dense you want to seed within each voxel in your mask. And in this case, we're having 1 seed in each voxel. Or this would be, I believe, 3 seeds in each voxel, because it's this is just a short form, but it's 1 by 1 by 1, because our voxel has depth as well. And now we apply our tracking algorithm. So we're using EUDX, and there's important parameters to include, which we already defined: the indices representing the directions of the peaks, the stopping criterion, the seeds, the affine, and the step sizes to take in tracking. So this is not where we actually compute the streamlines. This is just setting up the generator. So actually how we're going to propagate the streamlines. So we give it our peak indices. So we're telling it, here's a map, here's our data essentially, and at each voxel, here's the peak directions. So we feed it the peaks. We give it our stopping criterion. So we tell the algorithm, if you reach some value in this mask, stop tracking and end the streamline there. We're telling it where we're going to seed from, so where we're going to start propagating our streamlines from, the space we're going to do this in, the affine transform, and then the step size. And it's typically good practice to have the step size as a fraction of your voxel size. So for example, if you have 2 millimeter cubed voxels, so your isotropic voxels, your step size is probably going to want to be 1 or 0.5 or even lower than that. So you want to take multiple steps within each voxel. And the step size is essentially just when the algorithm is going to compute the next direction that we should move to when propagating the streamline. And then we generate the streamlines. So we use the streamlines function here from the dipy.tracking.streamline object. And then we feed it our streamlines generator, and then it will start tracking. And then once it's done, you have your deterministic set of streamlines using the UDX algorithm, which maps the human connectome or the tractography. So it's common to save these streamlines as a track.viz file, and it's typically loaded into other software. You can visualize it in Python, but it's not as interactive. So there's tons of other software to visualize these streamlines. And that's because how you get them back is essentially, they're what's called polylines. So they have vertices, and then we connect those vertices by a straight line. So you can imagine that our tracks can bend and curve in any which way. So we represent those by having multiple vertices along our track, and then we just draw a line connecting those vertices. So imagine just connecting the dots, essentially, is what we're doing. And so we have to have a different way to kind of visualize that. So there's plenty of softwares out there to visualize and look at your streamlines. But here we're going to save our tractogram using the stateful tractogram function and then the save tractogram function to actually save the file. So here we set up our stateful tractogram object. We give it our streamlines that we just calculated up here. We give it our original diffusion weighted image, kind of tells it what space we're doing this in. So it's gonna be in the same space as your diffusion weighted image. And then we're specifying, do we want our vertices in voxel space or what's called RAS space? So RAS space is subject specific, and it's right anterior superior, and that's relative to the scanner coordinates. Not super important, but it's important to note that you have to specify the space that you want these defined in. And finally, we can save the tractogram. So we give it the stateful tractogram object we just made, this SFT, and then we specify the out directory or where you want to put your tractogram results. And here you can see that the suffix here is .trk. And again, that's the track.viz file format, which can be read into many other softwares to visualize. But here we're going to show you how you can visualize them in 3D, in a 3D scene using the Fury package. So you make an actor with the streamlines and a color map. Then you generate the volume figure, and then you can plot the actual figure itself, and you can show it. And so here you can see we have the full brain set of tracks. So for example, the blue is superior to inferior on this coronal slice. So right in the brainstem here, we know we have a large bundle of tracks that come up into the brain. So that makes sense that this is superior to inferior. The red is left to right. And here you can see part of the corpus callosum here. So the highly coherent bundle left to right. And then green is anterior to posterior. So we have our set of streamlines using a deterministic process. And the final module we're going to talk about is the probabilistic tractography process. So probabilistic fiber tracking is a way of reconstructing the white matter connectivity like we just saw, except it follows the trajectory of a possible pathway in a stepwise fashion, and it propagates those streamlines based on the local orientations reconstructed each voxel, much like the deterministic process. However, with the probabilistic process, the tracking direction at each point is chosen at random from a distribution of possible directions that is centered on the main direction. So it's no longer deterministic because we are sampling at each point. At each vertex on our streamline, we're taking a different sample along the main direction. So if I run it with the same beginning parameters and I run a probabilistic process, we expect different outputs because we're doing this random sampling of a distribution. And the distribution at each point is different, and it depends on the observed diffusion data. So the distribution of tracking directions at each point is represented as what's called a probability mass function. And the possible tracking directions are restricted to a set of points that are distributed on the sphere like we saw previously. So probabilistic methods are very similar to deterministic methods in many ways. They start propagating from a seed map. They have seeds per voxel. And it's important to note that the higher number of seeds you put in a voxel, so the more streamlines you track from a single voxel, the larger number of potentially recovered long-range connections you will have. However, this comes at a cost of more computation and resources required and a longer running time. And so in the previous case, in the deterministic process, we just sampled, or we just used the tensor, which doesn't give us any measure of crossing fibers. So in this case, we're going to show you how to do this with the constrained spherical deconvolution process. And so again, this first bit of code is the exact same as we've seen. We get our data, we get our B values and B vectors, put them in a table, specify the affine, all the stuff we've seen previously. And again, we're going to create the seed mask, and we're going to use FA again to make our mask that we're going to seed in. And the same process, we're seeding in regions above 0.2. So we're binarizing 0.2, and we're going to set anything above that to 1, anything below that to 0. So we're making the mask, which we're going to propagate our streamlines within. And then we're setting that up. We're setting the seeds from mask up, giving it our mask, our affine, and how dense we want to sample. So how many seeds we want to put in each voxel, which will begin propagating the streamlines. And so we're going to now do constrained spherical deconvolution. So much like the module we talked about previously, we need to estimate our response function. So we give it our gradient table, our data, the FA threshold, everything we talked about previously. We're specifying the spherical harmonic order that we're going to use. In this case, we're using 2. And then we set up our model and we fit it. So once we get our response function, we can fit our constrained spherical deconvolution model. So we made our seed mask using FA, which is derived from the tensor, and we set everything above 0.2 to 1, saying that we're going to seed in every region that's above 0.2 FA. But in the case of the stopping criterion, we're going to use what's called the generalized fractional anisotropy. So one issue we saw with DTI is that in regions of crossing fibers, what it gives you back is a donut, right? It doesn't give you like an X. Was essentially saying that there is 2 crossing directions. It gives you what looks like a donut, and the FA in those regions is quite small. It doesn't think there's anisotropy in a voxel with crossing fibers, although we know there is. So generalized fractional anisotropy is derived from the ODF itself. So it's much more robust to crossing fiber measures than FA. And so we're going to use generalized fractional anisotropy as our stopping criterion to ensure that we're not stopping inappropriately in regions of crossing fibers where we still want to be tracking. We want to track those crossing fibers. We don't want to stop there. So here we get our generalized fractional anisotropy. And then we are fitting essentially the spherical harmonic reconstruction model. And we're setting our stopping criterion. We're using the threshold stopping criterion function here. And we're setting GFA to 0.2. So essentially it's going to, that's just specifying the same thing we saw previously, where it'll keep tracking in any GFA, generalized fractional anisotropy value that's above 0.2, and it'll stop tracking. It'll end the streamline at any value below 0.2. We're creating the directory where we're going to save our tractography results. And then here we're just saving the generalized fractional anisotropy image, and we're plotting it here. And so it looks much like the FA image, but as we discussed previously, it's more robust to crossing fiber orientations. And here again, you can see it's really high in the white matter, which makes sense because white matter is highly anisotropic. As we saw previously, the FOD, the fiber orientation distribution, derived from constrained spherical deconvolution, estimates the distribution of fiber bundles within each voxel. And we use this distribution for probabilistic tracking. As we saw previously, we put our FOD onto a discrete sphere. And so this discrete sphere is what we give to the probabilistic direction getter, and it makes the probability mass function for sampling the directions at each voxel. We need to clip the FOD to use it as a probability mass function because it cannot have negative values. Ideally, the FOD is strictly positive, but there can be noise or model failure sometimes, and it can have negative values, which the tracking process doesn't know how to deal with. So we have to deal with that ourselves. And we clip it. So the set of possible directions that we propagate the streamline with, we restrict it by a cone with angle theta, and that's named max angle in DiPi's probabilistic direction getter from the probability mass function method. So if we have a main direction, we're sampling a cone around that main direction, essentially saying we can track in any kind of distribution around that main direction. Although most of the time we're going to follow the main direction just on average, we're still sampling a distribution where we might follow a little bit of an oblique angle to that main direction. And so another relevant parameter of the propagation is the step size, as we saw previously, how much we're going to advance to the next point or how far of a step we're going to take before we sample the direction again. And then again, the stopping criterion, which tells us when we're going to stop tracking. And here we used generalized fractional anisotropy. So we fit our ODF onto what's called the small sphere. So we're discretizing that ODF and we're putting it onto a usable sphere and we're clipping it. So the minimum value is 0, no negative values here. And then we're feeding that into our direction getter, which is probabilistic from the probability mass function. And so we give it the max angle, which here we specified as 30 degrees. So consider it a peak. If there's no other peaks within 30 degrees, they have to be 30 degrees apart. We're giving it the sphere we used. And then we can feed that into the local tracking algorithm. So we give it our direction getter object, the stopping criterion, which is generalized fractional anisotropy, the seeds, which we used FA in this case, and we're seeding only in the white matter pretty much, anything above 0.2 FA, the space, and then the step size. So how far are we going to take a step in our voxel before we sample our distribution again and decide which direction the streamline should move. And then we generate our streamlines, and then we save them to the stateful tractogram object, and we're saving them as this trackviz file again, and except this time it's probabilistic. And here we're doing the same kind of visualization as we did with the deterministic process. So when you look at it as a whole, and you compare the deterministic and the probabilistic, sometimes there might not be that big of a difference. I mean, if I flipped back and forth between the two, you might be able to point out some differences in the streamlines, but generally they should be somewhat similar. So again, we're looking at the same orientations, and here you can see the high inner and outer orientation, or sorry, superior inferior orientation with the blue, the corpus callosum here, left to right, and then the green anterior to posterior. And so now we generated streamlines using this probabilistic method, which again is less sensitive to noise than the deterministic process because it assumes some kind of uncertainty exists. There's an issue though that is important to note with this probabilistic methods is that when you save this probability mass function, it takes up a ton of memory, a ton of RAM, because it has to save this probability mass function at every voxel. So the size of the probability mass function, or the FOD in this case, must be equal to the number of possible tracking directions on the hemisphere. And so every voxel has a unique probability mass function, and it has to save that into memory. So it's very intensive. And most of the time, unless you're tracking in a very small region, you'll run out of memory if you try to use the PMF when you track. So in this case, our FOD is 81 by 106 by 76, which is just the size of our data. And then the small sphere has 181 directions. So we have a fourth dimension that is 181 in size. So it's quite large. So we can avoid sampling the probability mass function and holding it in memory by building the direction getter directly from our spherical harmonic coefficients that we talked about previously, the basis function that we can represent any spherical function with. So we can also use a larger sphere when we use the spherical harmonic representation, because we don't have to worry about memory problems. So we can expand and take and sample more points along the sphere, which should ideally give us more accurate directions. So in this case, we're using the default sphere, which has now 362 directions, which is greater than what we used previously with the small sphere. And we don't have to worry about memory limitations because it just has to save a few coefficients at each voxel to represent the whole spherical function. So the process is pretty much the exact same, except now we call with the probabilistic direction getter, we say from spherical harmonic coefficients instead of from probability mass function as we defined here. And then we give it the spherical harmonic coefficients from our constrained spherical deconvolution. You can call it just by using the object that you use to actually fit it, dot spherical harmonic coefficients, or SHM underscore COEFF. The max angle. So again, what is reasonable for us to continue tracking? Anything above 30 degrees is essentially, or anything below 30 degrees, we can't keep tracking. The sphere we're going to use. And then we're going to generate the streamlines with the exact same process as we talked about previously, using the same stopping criterion, seeds, affine, step size, all the same, except now we generate our tracks with spherical harmonic coefficients. And if we look, it looks pretty much, it looks very similar at least to the probability mass function method, except now it was much less computationally expensive to generate by only saving a few coefficients instead of the whole function. And so if you're going to generate probabilistic streamlines, the best bet is to use the spherical harmonic coefficients to save memory and make sure it doesn't take too long to run. So not all models in DIPI have the spherical harmonic coefficient attribute because not all models use that basis to represent the data internally. However, you can fit any ODF, any spherical function using spherical harmonic coefficients. So if we get the peaks from model here, all the stuff that we've seen before to get the peaks from model, and you can set this return spherical harmonic to true, and then you can save those. You can save those peaks essentially and check that the orientation information conforms to what is expected. So it's always important once you use constrained spherical deconvolution to quality control or quality essentially check that those ODFs don't look odd, right? So if you look in the corpus callosum, they should be very highly oriented and there should really be only one peak and they should be oriented in a relatively coherent fashion. So it's important to check your results and make sure that your ODF was actually calculated properly. And here we're just seeing the peak vectors. And if you'd zoom in, you would see that they do look pretty good. And they are, in like, for example, in the white matter, they are coherently oriented in one direction. And it seems to be reasonable, which should give you confidence that the FODF was calculated properly. And now you can use those peaks to perform the tracking process, which is essentially the exact same thing again, except we're using those peaks. And again, the results look quite good. They do look pretty similar to the other ones as well. So I believe that is it. This is just a tip if you're interested in reading to make sure your tractogram is well aligned with your data and how to view your info, make sure everything looks good. Very important to quality control your data. So is there any questions? Any questions right now?
Yes, I was actually wondering whether you could explain global tractography, because I kind of didn't understand what that is about.
Yeah. So local tractography is essentially the branch. It's a large branch of algorithms, mainly deterministic and probabilistic. So the two that we just saw would be considered local tracking algorithms. And essentially you can think of local as voxel-wise tracking, right? So we seed in a single voxel and we start following those directions, right? And so it's called local because we're in a single voxel in a single neighborhood and we start making a streamline, either by deterministic or probabilistic processes. And so that's essentially the idea behind local tracking is we model the white matter by creating streamlines from the local direction information at each voxel.
Thank you so much. What about global? So how does global work?
Yeah, good question. So global, it doesn't seed from a single voxel and then start tracking the local direction information. It finds a global optimal solution about what connects regions at once, essentially. So with global tractography, you find your full track configuration essentially at the same time. So you track your fibers simultaneously. So a benefit of that is an issue with local tracking with probabilistic methods is you're less likely to get longer tracks. Probabilistic is biased to stopping early, essentially. And it's also more sensitive to local noise, while global tractography tries to overcome this. Now, the process that global tractography uses, like the actual algorithm, is a bit more complex. It has to do with it brings in theory from fluid dynamics and essentially pretends you let a molecule just run. If I put a water molecule in a single voxel and let it run with our local direction information, what happens? But essentially, it just does it all at once, is what you can think. The difference between global and local is global finds an optimal solution. Yeah, no worries.
Yeah, thanks.
Is there any other questions? Doesn't have to be about tractography either. Any other questions that you thought of from the rest of the content, if you're curious about anything? Okay. Well, hopefully that was informative, and I hope you all learned something and maybe take the time over the next few days to really process everything. I know it's a lot. It's hard to fit diffusion and tractography and all this stuff into one single session over a few hours. It's quite a complex process. I've been reading about it for years and still don't understand it. So it's a long road, but hopefully this is a good start. And hopefully the workbooks that we gave you can help start with your diffusion learning. Cool. I don't know if there's any other announcements. Aaron or John, anything to remind everyone of?
There is the post workshop survey that people or attendees are expected to fill in, just so that we know where we can improve. So you are all invited to fill in that survey. Thanks.
All right. Yeah. Thank you everyone for coming, and have a good day. Hopefully see you all later.
Bye.
So
Thank
see you
you.
all next week. Thank you.
Bye.
See you. Bye.